Sorry. Okay, so this is where we stopped from my previous lecture. So I was about to prove these three propositions. First one is, well, if any square matrix has an inverse, then it must be unique. And number two, so I was about to prove proposition number two. So it basically says that being able to have an inverse is mathematically the same as A having the full set of non-zero pivots. Possibly, if necessary, then you will need to do the row exchange. But you have the idea. You know the idea. And I proved the only if part from the previous lecture. And now I'm about to prove the other way. So under the assumption that A has full set of non-zero pivots, I want to prove that there is a inverse. Okay. Oh, before I do that, before I prove this, then you have to remember that if A has a full set of pivots, possibly row exchanges, then AX equals to B has a unique solution for every possible choice of B. You remember this? Okay. All right. If you can remember this, then, well, I can make it very quick. All right. Now, let us consider this. AX is EI. Oh, my EI is almost every entry equals to 0, but the ith one is 1. But the ith entry is 1. Sorry. I want to consider this system of linear equation. And because since we have assumed that A has full set of non-zero pivots, therefore, this system of equation must have a solution, must have a unique solution, right? Has a unique solution. I will name it xi. I am not only considering this system of equations, but I am considering all possible equations from index I varies from 1 to n. I have n such systems, right? And they all have the solutions from x1 to xn. So therefore, I have n such solutions from x1 to xn. Now what? I want to introduce another n by n matrix such that each column of the matrix consists of solutions of the systems. So the first column is this is a column vector, right? So the first column is the solution of when I equals to 1, and second one is the solution when I equals 2, and all the way up to xn. And this is an n by n matrix, right? This is an n by n matrix. I'm gonna call it, I'm gonna call it B. Can you imagine such a matrix? Yeah. So that every column is solution of these systems. Now, what happens if I multiply this matrix to the right of A? Then the resulting matrix is the resulting matrix also has n columns, and each of the column is this is A times x1. The second one is second column is A times x2. A times xn. right? Because the A times first column goes to the first column of the resulting matrix, and A times second column goes to the second column of the resulting matrix, and so on. So this is your resulting matrix. Okay, and but now I can say this is E1 En. These vectors are very special, so it has its own name. So we say this is a standard unit vector. Even if I do not know what unit means. But these are, well, so this is a matrix, and each of these columns is a standard unit vector. So therefore, it must be the identity matrix, right? Okay, good. Now I'm gonna use the same logic for somehow different looking system of linear equations. A is still n by n matrix, and Y is 1 by n matrix, and B is another 1 by n matrix. I want to claim that this is another version of system of linear equations. Why? So Y1, Y2, Y and B, they are row vectors, not column vectors, row vectors, sorry. Times A is B1, B2, Bn. So this is 1 by n row vector multiplied by n by n vector. So therefore, the left-hand side is another n by n row vector. And I want these two guys are the same vectors. In order to do that, then every component of this vector must be the same as every component of that vector. So this is a system of linear equations, right? And because we have assumed that A has full set of non-zero pivot, therefore, by the same logic, for every possible choice of row vector B, I must be able to find a one unique solution Y for every possible choice of B, right? As a unique solution for every possible choice of B. Okay. Just try to consider the LU factorization of your matrix A. Then I guess you can be easily convinced. Okay, so that means if I replace the right-hand side of this equation by Fi is another version of the standard unit vector. So each of the columns, so almost every column equals to 0, but the ith one. So ith column equals to 1, and all the other guys, they are 0. And if you replace your B by this row vector, Fi, then because of this system of linear equation must have a unique solution, right? Unique solution Yi. Okay. Again, I have n such systems from I is 1 to n, and by similarly, I consider another matrix, another n by n matrix, such that whose rows are nothing but the solutions of these systems. And if I multiply this matrix by A, then the resulting matrix would be F1, The rows of the resulting matrix must be from F1 to Fn, right? This is what? This is the identity again. I want to call this guy C. Okay, so now I have two matrices B and C, such that A times B is the identity, and C times A is the identity. Let us consider C times A times B. By associativity, if I multiply ACA first and B later, then is I times B, which is B. And on the other hand, if I try to multiply AB first and C later, then this is C times I, which is C. Therefore, B, C is B. C is the same matrix as B. Okay, so therefore, this matrix must be the inverse of A. So I was able to find the inverse of A. Okay, so then this is the end of the proof of proposition number 2. Isn't that surprising? Yeah, for me, this is very non-obvious result. Why? Because I got some matrix just by solving bunch of these systems, and I have another matrix by solving another system. And somehow some miracle happens, and those two matrices turns out to be the same thing. Well, at least for me, this is a very surprising result. Okay. Anyway, so I got the inverse. So I have the inverse. Now, I want to prove the proposition number 3. Ax equals to 0 has a unique solution if and only if A is invertible. By the way, if your right-hand side of equation equals to 0, then your system always has a solution. You're guaranteed to have one solution. What is that? A trivial solution, right? If you plug in x equal to 0, then that is automatically going to be the solution, right? And the statement says, if A is invertible, then that trivial solution is the only solution that you can find. There is no other solution, right? That is the claim of the proposition number 3. And let me prove this. Okay. And number 3, I guess this direction is easier than the other one. Suppose that A has an inverse matrix. Then I can multiply the inverse of A to the left of both sides of the equation. Is A inverse of 0. And if you multiply any matrix by 0 column vector, then the answer is automatically the 0 column vector. And this is X. Therefore, X must be 0. So it means if your A is invertible matrix, then the only possible solution of this equation is X equals to 0, the trivial solution. Okay. Okay, this is good. Now the other way. Let us suppose that A X has a unique solution. Now I want to show that A must be invertible. How? How? I want to prove this by using contradiction. Suppose not. Suppose that A is not invertible, then what happens? Then let me just for this moment, let me go back to proposition number 2. So inverse exists if and only if A has full set of non-zero pivot, and that implies that if A does not have inverse, then that means A does not have full set of non-zero pivots. Okay. So then A does not have a full set of non-zero pivot. Okay, then what kind of contradiction can I derive from this? Ax equals to 0. Since there is no full set of, even if there is no full set of pivot, but I can still try to complete the fourth elimination just by using elementary row operations, right? Then I can try to decompose A as a multiproduct of L times U. Here, this L is a lower triangular matrix whose diagonals are all ones, but U is not, right? Since A does not have a full set of non-zero pivots, so therefore, on some diagonal entry of U, you should be able to find some zero numbers on the diagonal, right? So P11, P22, so UX is so basically you're supposed to solve this equation, this system of this equation. And I want to claim that this last entry, this one must be 0. Why? Why is that true? Because well, if you apply elementary row operations, then every time you apply elementary row operation, the number of non-zero entries of every column decreases by 1. Always decreasing. Well, it decreases at least by 1, right? So and here, not being able to have full set of pivot implies, therefore, the last entry of your diagonal matrix must be 0, right? Right? Now, what happens? What kind of contradiction can I have here? In this case, your xn can be any number. No matter which number you plug in for xn, that's still going to be the solution. Solution of this, and which is the solution of that, right? This means solution of your equation is not unique. Okay. So therefore, this is a contradiction. Why? Because we have assumed that AX equals to 0 has a unique solution. All right, so the proof is done. Yeah, I have spent too much time on explaining this proposition, but I can try to summarize this entire thing in just a single sentence. A is invertible is mathematically equivalent to say A has a full set of pivots, which is again mathematically equivalent to say AX equals to 0 only has a trivial solution. Those three things are all the same thing, at least in mathematics. Yeah, so A, well, yeah, here obviously A is a square matrix. A is invertible matrix. If and only if A has a full set of non-zero pivot, and if and only if AX equals to 0 has a unique solution. Okay. This statement also gives us very useful criteria. If you want to, well, especially if you want to determine any given square matrix is singular or not. How do you know any given matrix allows an inverse? Sorry, by the way, matrix is singular means that matrix A doesn't have an inverse. If I say matrix A is non-singular matrix, then that means a matrix A has an inverse. Non-singular means has an inverse, and singular means doesn't have an inverse. Okay, so how do you know any given square matrix has an inverse? I mean, by the idea is just try to apply the forward elimination of the matrix, just using the Gauss elementary row operations. If you can have full set of non-zero numbers, then that matrix is invertible matrix. But if not, then the matrix is not invertible matrix. Okay. Okay. Good. What's next? Here we have also another very interesting theorems on the LDU factorization. Well, in some textbooks, so they argue, well, in some textbook, the author says that LDU factorization of some singular matrix is also possible, but at least in this course, in our textbook, LDU factorization is only possible for non-singular matrix. So let me suppose that A is a non-singular matrix. Suppose I have a n by n square matrix that allows a LDU factorization. And let me say I have these two LDU factorizations. Oh, well, because of the definition of the LDU factorization, these L1 and L2, they must be the lower triangular matrices whose diagonals are all ones. And U is the upper triangular matrices with diagonals are all ones. And these are D1 to D2, they are diagonal matrices. And this proposition says, in this case, L1 is L2, U1 is U2, and D1 is D2. In other words, if you try LDU factorization of any given matrix, then the answer must be the same. Okay, so LDU factorization is unique. Why? First, you should be able to see that the lower triangular matrices and the upper triangular matrices they are all invertible. Why? Because by its definition, they are lower triangular or upper triangular matrices and whose diagonals are all ones, right? That means, in other words, these matrices have non-zero pivots, full set of non-zero numbers on their diagonals, right? So they're invertible matrices. So I can think of their inverses. L1, D1, U1, L2, D2, U2. These two things are the same. And let me multiply both sides of this equation by the inverse of L2 on the left. Then L2 inverse L1, D1, U1 is D2, U2, right? Also, I want to multiply the inverse of U1 to the right of these, right to the both sides of the equation. Then I will have U1 inverse like this. Okay. Good. Now what? Okay. These are lower L2 and L1. They are all lower triangular matrices, right? And these the diagonal matrix, and diagonal matrix is also a lower triangular matrix. Therefore, the left-hand side of this equation is a lower triangular matrix. And on the other hand, these two guys are upper triangular matrices. And the diagonal matrix also an upper triangular matrix. Therefore, multiple of these three matrices is another upper triangular matrix, right? This is very interesting phenomenon. So the lower triangular matrix is the upper triangular matrix. Then only possible explanation is these two guys must be the diagonal matrix, right? Has to be, they must be diagonal matrix. Okay, good point. And also the diagonal of this guy, but they are all ones, right? Diagonal of this guy, they are all ones. Therefore, diagonal of these two matrices, they are all ones. Therefore, if you multiply this guy by this, then diagonal matrix of this side is the same as the diagonal entries of this. So diagonal entries of this guy is the same as diagonal entry of this one, right? And therefore, this one must be D1, right? And by exactly same reasoning, this one must be D2. Okay, so L2 inverse L1 D1 is D1, and D2 U2 U1 inverse is D2. Therefore, multiplying the inverses of D1 and D2, is identity, and U2, U1 is identity, right? And my claim is done, right? So D1 is D2, and L1 is L2, and U1 is U2. Okay, so proof is done. Great. L1, L2, U1, U2, and D1 is D2. All right. So this is about the uniqueness of the LDU factorization. Oh, just one more thing. So one more warning. Well, the LDU factorization is unique, right? But sometimes, well, but PA is LDU factorization main. So, but if you tried any low exchange towards the original matrix A, then LDU factorization may not be unique. Why? Because permutation if you have applied two different low permutation, then the left hand side of your matrix, left hand side of the matrix itself, it changes. Therefore, LDU factorization might be a little different. So, well, so this is very important point. But the LDU factorization of matrix is unique as long as you have not applied any low exchanges. If you use any low exchanges, then LDU factorization may be unique. May not be unique. Sorry. Okay. Suppose I have two n by n matrices. If A and B, they are both invertible, then their product is also invertible, and its inverse is B inverse times A inverse. So the order reverses, is being reversed. So this is the low, well, this is about the inverse of the product matrix. The proof is very easy. Just try to multiply A inverse B inverse to the both sides of B inverse A inverse of your equation. Then B times B inverse, this is identity. So you can cancel these two guys out, and A times A inverse, which is another identity. And by same reason, this is identity. So therefore, the inverse of A times B is B inverse times A inverse. Good. The next proposition is again about the inverse matrix. Well, typically, finding inverse of any given matrix requires a lot of computation. Very computation demanding algorithm. So usually, in computer science, we usually do not attempt to find the inverse, explicitly find the inverse of any given square matrix. But if the dimension of your matrix is small enough, then finding the inverse of any matrix is sometimes doable. Especially in 2x2 case, A, B, C, D, then finding inverse is very easy. If A is invertible, in other words, A is non-singular, if and only if AD minus BC is non-zero. So how do you know any given 2x2 matrix is invertible or not? Just try to multiply this guy by this minus this guy by that. If that number equals to 0, then you cannot find this inverse. But if non-zero, then you can try to find this inverse. And there is a formula for inverse of 2x2 matrix, which is which is this. If you have not memorized this formula, the inverse of 2 by 2 matrix, then I guess this is the right time to try to memorize this. Very important one. Well, personally, so I was introduced to this formula when I was a high school student, and I still remember it, even 30 years has been passed. So this is very good. This is very useful. The proof is very easy. A, B, C, D. The proof is, well, just try to multiply these two matrices. This is an easy computation, and you can easily be convinced that this AD minus BC and 0 and 0, and again AD minus BC. So this is AD minus BC, everything multiplied by the identity matrix. So well, the conclusion is, so if you multiply the both sides of this equation by AD minus BC, then it turns out the inverse of this matrix is precisely this one. But however, if this number equals to 0, then you can never try to divide any number by 0. Then you cannot. So therefore, in that case, the inverse does not exist. Okay. All right. Okay. Good. So now we know how to find the inverse of 2 by 2 matrix. How about inverse of 3 by 3 matrix? Do you know how to find the inverse of 3 by 3 matrix? Maybe yes, maybe no. And for those of you who do not know how to find the inverse of some larger square matrix, then I believe it will be really great to introduce you so-called the Gauss-Jordan method. So what is Gauss-Jordan method? Gauss-Jordan method is an algorithm that finds the inverse of any given square matrix. How? Okay, great. So what is Gauss-Jordan method? And how Gauss-Jordan method finds the inverse of any square matrix? To explain the idea, I will need to go back to the proof of this proposition. Okay, look at so if you look at the proof of this, then so this matrix B, this matrix is actually the inverse of my matrix A. And it turns out every column of the inverse, every column of this matrix is nothing but the solution of this system, right? The first column is the solution of this, E1, and second column is solution of, well, E2, and so on, right? So that means if you can solve n such a system from when n equals to 1 to n equals to n, then that means you can find the inverse of the matrix A, right? So this is the idea. So basically, so if you want to find the inverse of A, then you will need to solve this system, n such systems, right? From I equals to 1 to n. But solving the system n times may take too much time and effort. So the idea is, try to solve all these systems simultaneously. How? Ax equals to b. This is a system of linear equation. This can be translated, well, in terms of matrices. This can be translated to this, right? And again, you know that these unknowns from x1 to xn, they are somehow irrelevant when you're actually solving the system, right? So just by getting rid of this x1 to xn, then I can translate this one as so-called the augmented matrix. Do you remember this? So this is what we call the augmented matrix. But it contains all required information to solve this system, right? Now, how do we solve this system? Well, obviously, we need to apply the elementary law operations. So if you apply the fold elimination method, then we can convert this guy to be upper triangular as well, especially the right-hand side of this augmented matrix, left-hand side of this augmented matrix to be upper triangular matrix by applying bunch of elementary law operations, right? But this is not the solution of this equation, this system. In order to get the solution, then I will need to put another effort. How? First thing is that you just divide each of these laws by this leading coefficient. You know, dividing any equation by some non-zero number is completely allowed. It's just a part of the elementary law operation, right? So if you multiply, so if you divide each of these laws by these leading numbers, then your diagonals are going to be all ones, right? Now you have bunch of ones on your diagonals. Now you apply another set of elementary law operations so that you get rid of all these numbers. If you can do that, then this is what you get. All the way ones and some other numbers on the right, right? And I claim, and if you translate this into the world of matrix, then that means one identity times x1 to xn equals to something. This number is the something, and I claim that this number, this column, is exactly the solution of this original system. Right? Right? Okay. So this is how I solve any given system of equations only by using elementary law operations. Therefore, and I want to solve all these systems simultaneously. How? Now I am introducing this looking augmented matrix. Well, if the dimension of this guy was n by n, then the dimension of this guy is to be n by 2n, right? And the right-hand side of this augmented matrix consists of all the standard unit vectors from E1 to En. And so this is nothing but the identity matrix. The right-hand side is exactly the identity matrix. And if you apply a bunch of elementary law operations so that left-hand side is the identity matrix, then what is this? This guy is the solution of AX equals to E1. And this invisible guy, second column, is the solution of AX equals to E2, and so on. Therefore, the matrix on your right must be the inverse of A. Right? This is the idea of the Gauss-Jordan elimination, Gauss-Jordan method. So clever, isn't it? No? Well, this is too obvious. Yeah, everything is too obvious. All right, so this is the idea. And I told you the linear algebra, the theorems and principles, they are all important, but linear algebra is basically about computation. So I'm going to show you the computation and I'll show you how to find the inverse of any given matrix. Suppose that this is my matrix, 2, 1, 1, 4, 2, 0, and -2, 7, and 2. I have this matrix, and I want to find the inverse of this guy. All right. To do this, now I want to introduce an augmented matrix that looks like this. These dots represent 0. Okay, so this one should be my starting point. And now I apply the now I want to change the left hand side to be the identity matrix. To do that, first I will need to eliminate these two numbers. How? By multiplying -4 to the first row and add it to the second, and by multiplying +1 to the first row and add it to the third. Then I get is 2, 1, 1, 1, 0, 0, and 2 is -2 and -2 and 1 and 0, 8 and 3 and 1. Right? Okay. Oh, now I'm in trouble because I have 0 on the diagonal, so I cannot proceed any further. So unless I apply the elementary row exchange, right? So I will need to exchange these two rows. So it now is 2, 1, 1 just carries over 1, 8, 3, 0, 0, -2. And 1, 1, 1. Okay. Okay. Good. Now what? Oh, and now I want to make all these diagonals to be 1. So I divide everything by 2 for the first row, and 8 by the second, and -2 by third, just like this. Okay. Okay. All right. Now what? Now I multiply the last row by -3/8 and add it to the second. Then I can eliminate this number. And I multiply the last row by -1/2 and add it to the first can. Then I can get rid of this number too. I want to make it quick. So it is 1/2 dot dot 1 dot dot dot. I want you to do this computation by yourselves. Yes.
If we calculate 행연수 말고 열연산으로 똑같은 A 인버스가 나와요.
열 연산을 어떻게 한다는 거죠?
그러니까 이 행과 행에다가 뭘 곱해가지고
네.
exchange를 하는 기본 행 연산인데
네.
그랑 비슷하게 열도 똑같이 하면 똑같이 나오고.
그렇게는 안 되죠. 네. Yeah, okay, good point. Well, he was basically asking, so what happens if we try the not elementary row operations, but elementary column operations? That is very interesting question. But if you want to solve some system by elementary column operations, then your system is somehow be transposed. Oh, even though I have never mentioned about the transpose, but in that case that is possible. But for this problem, no. Yeah. Thank you. Good point. So yeah, let me finish my computation. So I was somehow lost. Okay, now I know. Okay, sorry, I'm good. I'm good. Negative 1/4, 3/6, 1/8, 1, negative 1/2, and 0, and yeah. So, all right. That. And this one is the A inverse. So if you're not convinced, try to multiply this matrix by this. Then you should be able to get the identity. Okay. All right. Oh, sorry. Oh. Now I can introduce the transpose. Okay, what is A transpose? Well, A can be matrix of any dimension. So A can be any rectangular matrix. A is, so say that A is n by n matrix, and the transpose AT. So well, the transpose matrix is, so we usually, so the transpose matrix is denoted by A superscript T. Yeah, obviously this T represents the transpose. So what is AT? AT is, the transpose matrix is, well, n by n matrix. You know, so the original matrix, so if your original matrix was n by m, then these two numbers, the column number and row number, they are being interchanged. So n by n matrix, and which is defined as ij entry of this transpose matrix is the same as ji entry of the original matrix. If you do not understand this explanation, then why don't you just why don't you just look at this example? If this is my original matrix, then row number, column number is now being interchanged, and everything has been flipped about the diagonals. You know what I mean? So this is what I mean by taking transpose. Okay, transpose is very easy. And there are some interesting properties on the transpose. A plus B transpose is A transpose plus B transpose. I guess this is very obvious. I don't need to prove this. Do I? No. But the next one is somehow interesting. If you take transpose of product of two matrices, then it is the same as B transpose times A transpose. And the last one is if A is invertible matrix, so that means A is n square matrix. If square matrix A is invertible, then its transpose is also invertible, and this inverse matrix is the same as inverse transpose. Isn't that amazing? This last property is very interesting because, well, so roughly speaking, so inverse operator and transpose operators, they are somehow completely interchangeable, right? The order doesn't matter. Okay, I am not gonna prove number 1, but I will prove number 2 and 3. Okay. This is clear. And number 2, let A be Aij, and B be Bij. Oh, sorry, I forgot to mention the dimension of A and B. let me say A is m by n, B is m by L. Yeah. So these two numbers, they agree. So I can multiply these two. Okay. And if I multiply these two matrices A, B, then ij entry of this matrix, well, according to our definition, is aik and bkj. Yeah. Yeah. Okay. All right. Okay. Now, on the other hand, I want to multiply B transpose and A transpose. This is L by M. This is M by N. Okay. Okay. I am especially interested in ij component of this matrix. What is this? Then again, k from 1 to m is the the ik component of the B transpose and kj component of A transpose, right? By definition of the matrix multiplication. But B transpose ik is B ki, right? And A transpose kj is ajk. These two indices, they agree. Oh, okay. Oh, good. Yeah, this is not a multiple of two matrices, but this is multiple of two numbers. So I can always free to swap these two, just like this, right? Then this is what? This is ji component of A times B, right? And what now? Okay. This is ij component of AB transpose. Okay. Okay. Now I'm done, because now for any ij entry, the entry of this matrix is the same as the entry of this matrix. So therefore, these two matrices, they must be the same matrix. So BT, B transpose, A transpose is AB, everything being transposed. All right. Since now we have property number 2. Let me prove the last property. Okay. This is easy. So I multiply A transpose times A inverse, everything being transposed. Then this is, because of the property number 2, I can say this is the same as A inverse times A transpose, right? If you transpose, then the order reverses. And this is clearly the identity transpose, but if you transpose the identity, nothing changes. And A inverse transpose times A transpose, which is the same as A times A inverse, everything being transposed, is again the identity. So this means if you multiply this matrix to the left or right of the A transpose, then you're going to get identity. This implies T inverse is A inverse transpose. It's a very convenient property. Transpose and inverse, they really don't care about the order. Everything is interchangeable. Okay. All right. here the identity matrix has very interesting property because it is actually invariant under transpose. Okay, if you transpose the identity matrix, then it is the same thing. It doesn't change. Such a matrix is called the symmetric matrix. A matrix is A is symmetric if the transpose is the same as the original matrix. So intuitively, you should understand symmetric matrix like this. So if in order to be symmetric matrix, then your matrix must be square matrix, right? Every rectangular matrix cannot be symmetric. And also, in order to be symmetric, you are free to have any diagonal entries you like, but all the other entries, all the off diagonal entries must be symmetric about the diagonal, right? So that is the symmetric matrix. Okay. There are very interesting way to build any symmetric matrix. For any matrix, so R can be any rectangular matrix. For any n by m matrix R, then if you multiply the R transpose to R, then they are symmetric. Right? How do you know that? Just take a transpose of this product matrix, this matrix, then you can be easily convinced that transpose of this guy is the original one, and transpose of that guy is still the original one. So this is how you get the symmetric matrix. All right, and for the symmetric matrix, it has very interesting properties regarding LDU factorization. Suppose I have a symmetric matrix if A has a LDU factorization, then the LDU factorization turns out to be LD and L transpose. Oh, why? Speaking of LDU factorization, so in order to have an LDU factorization, B is a diagonal matrix, and B is the diagonal, and L is lower triangular, and every diagonal equals 1, and U is a upper triangular matrix whose diagonals are all ones, right? But if you flip if you transpose L, then this is going to be L transpose is going to be the upper triangular matrix whose diagonals are all ones, right? So this is again, therefore, and so if you believe in the proposition, then the LDU factorization of a symmetric matrix has very interesting form, right? The proof. Well, suppose A has an LDU factorization, then and A is symmetric, therefore A is the same as A transpose. And if you take a transpose of this LDU factorization, then U transpose, D transpose, and L transpose, which is U, D, L. Because if you take a transpose of the diagonal matrix, then it is the same thing, right? So this is basically the transpose LDU factorization. Well, and this is the lower triangular matrix, diagonals are all ones, and this is upper triangular matrix, diagonals are all ones. So this is basically the LDU factorization of A transpose, right? But A has LDU factorization, which is LDU. And because of the uniqueness of the LDU factorization, L must be U transpose and U must be L transpose. Okay. So L must be U transpose. Okay. All right. All right. So this is so much for chapter 1. Now we will be turning to chapter 2. The title of chapter 2 is the vector space. Well, although the name scares me a little bit, but well, there's nothing to worry about. So we will still be interested in solving the systems of linear equations, But this time around, instead of trying to solve n equations and n unknowns, but this time around, the dimension of A may not be square matrix. A can be a matrix of any size. So for instance, you can try to solve a system AX equals to B such that the dimension of A is somehow is wide. A can be wide matrix. So okay. No. Sorry. So I forget. Sorry. We want to solve AX is B. Well, if the dimension of A is a square matrix, then that is about solving n unknowns at n equations, right? But what if your matrix A is a wide matrix? Wide matrix means number of unknown is greater than the number of equations, right? So in that case, since number of constraint is greater than less than the number of unknowns, therefore solution may not be unique. Okay. On the other hand, the dimension of A, the matrix A can be the narrow matrix. In that case, number of unknowns is less than the number of equations. In that case, typically you may not be able to find any solution at all, right? Now, how do we deal with such cases? This is what we are going to do in chapter 2. But well, basically, we are still interested in solving systems of linear equations. Okay. All right. The first section is 2.2.1 is about the vector space and subspaces. Do you remember the definition of vector space? Well, you don't need to write it down. Actually, you don't need to write down anything in my lecture because I am unloading my lecture note. This is basically the definition of a vector space. What is vector space? So, roughly speaking, the vector space is a set that has a vector addition and scalar multiplication. With reasonable associativity and commutativity and distributivity. So this is a vector space. We say this is V is a vector space over R, real numbers. This is the easiest, one of the easiest example. The n-dimensional space, well, we are mainly interested in this space, or R infinity. So this is nothing but the collection of all infinitely many tuples of real numbers. Well, this is somehow very, this is not that useful, but you can still consider addition or scalar multiplication. And also, this is also interesting. M by n of everything R. So what is this? This is space of all m by n matrices. If two matrices have the same dimensions, then you can add or subtract. And of course, you can consider the scalar multiplication. So this is clearly vector space. And space of all continuous functions on some certain interval is again a vector space, right? All right. And now, subspace. Suppose I have some vector space. V is a vector space. Some subset of V is called a subspace. What is this? If U and V is a member of S, then U plus V must be also a member of S. And if U is a member of S, then any scalar multiple of U must be also a member of S. So if these two properties are true for this subset, then we say S is a subspace of vector space, ambient vector space V. So, well, basically, the being subspace is the same as your subset S is, if your subset S is closed under vector addition and scalar multiplication, then you're good to say your subset S is not merely a subset, but a subspace. This is what I mean by subspace. Okay. There are very interesting examples on the subspaces, like if V is a set of all n by n square matrices over R real numbers, then these are some interesting subspaces of vector space V. Space of all n by n symmetric matrices. So addition of two symmetric matrices is another symmetric matrix, and scalar multiple of any symmetric matrix is again a symmetric matrix, right? So this is clearly subspace of vector space V. What about space of all lower triangular matrices? That is also true. If you add two lower triangular matrices, then answer is another lower triangular, and scalar multiple of lower triangular matrix is another lower triangular matrix. Therefore, it is also subset of vector space V. And sorry, I know I just ran out of time, but just give me just one more minute. Thank you. What about this? I have randomly chosen k vectors from Rn, and a span of these vectors. What is this? Do you remember this? A collection of all vectors that can be written as a linear combinations of from V1 to Vk. Is it a vector space? Yes, right? This is clearly vector space. Okay. This is very important vector space. And these are some non-examples. What is this? This Rn plus is a collection of all vectors such that every component is non-negative numbers, non-negative. Is it vector space? So vector subspace, a subspace of Rn? No, because choose any random guy from here, and if you multiply, if you take a scalar multiple of some negative number, then the result would be out of the space, out of this set. So therefore, this is not closed under scalar multiplication. So this is not a subspace. What was this? So this is basically a parallel translation of span of V1 and V2 by vector V, right? This is not a vector subspace. This is not a subspace. Why? Because there can be many explanations, but I just ran out of time, so I will make it very quick. So every subspace must contain a zero vector. Zero vector is contained in every subspace, right? But, well, intuitively, so if you parallel translate this space by vector V, then it may not contain the zero vector, right? So therefore, this guy cannot be a subspace. All right. So this is for today. See you next time. Bye.